The topic is pedestrians, crosswalks, and intersection control. We begin by recognizing that the street crossing experience comes down to the behavior of the pedestrian, the behavior of conflicting motorists and cyclists, plus the design of the intersection or crossing. The conflicting behavior of interest is whether motorists and cyclists yield for pedestrians. The behavior is influenced by a variety of factors, including the speed of travel. A motorist traveling at a slower rate of speed has more time to see, react, and stop for a pedestrian than someone who is traveling faster. The number of pedestrians may also influence yielding behavior. High volumes of pedestrians tend to raise motorist awareness of the likelihood of a pedestrian crossing the street. In this presentation, we focus on accommodating pedestrians at intersections, plus current practices concerning crosswalks and related intersection controls. Key topics include unmarked crosswalks, pedestrian warrants for traffic signals, 15th percentile walking speed, minimum pedestrian crossing requirements, and pedestrian signal intervals, particularly how they relate to vehicular intervals. In 2000, Thomas Jones and Patrick Tomczyk were motivated to study pedestrian accidents in marked and unmarked crosswalks. It had been the practice of the Los Angeles Department of Transportation to be selective regarding the reinstallation of marked crosswalks at unprotected locations. When removed due to resurfacing, painted crosswalks were not automatically reinstalled. By removing marked crosswalks at locations where they were not deemed appropriate, LADOT was seeking to reduce pedestrian-related accidents. However, citizens in the media challenged the practice of selective versus automatic reinstallation, saying it created an unfriendly pedestrian environment. What do you imagine they found when they evaluated unprotected crosswalks and compared accidents in marked crosswalks versus accidents in unmarked crosswalks? First, let's take a moment to review the basic concepts that frame the issue. The term unprotected refers to a legal crossing at an intersection where neither stop sign nor traffic signal is placed to control conflicting vehicles. The LADOT had been following the policies of the State of California Traffic Manual, which states, crosswalk markings serve primarily to guide pedestrians into the proper path and should not be used indiscriminately. We know that the California Vehicle Code requires that drivers yield right-of-way to a pedestrian crossing the road regardless of whether the crosswalk is marked or not. In essence, there's a crosswalk between every corner, whether it's painted or not, unless the pedestrian crossing is explicitly prohibited. Does it surprise you to learn that Jones and Tomczyk found that crosswalk removal was associated with a decrease in pedestrian accidents? Do marked crosswalks tend to give pedestrians an impression of personal protection, one that potentially lessens their sense of responsibility for a safe crossing? Jones and Tomczyk found the association to be significant enough to support the continued policy of selective reinstallation of marked crosswalks at unprotected locations. Special circumstances for marking crosswalks at unprotected locations include locations with frequent pedestrian usage, such as transit stops, institutional buildings, and active retail areas. At unprotected crosswalks, motorists yield, or pedestrians wait for an acceptable gap. If pedestrian and vehicular volumes are high, such that vehicle-pedestrian conflicts are frequent and difficult to avoid, signals may be warranted. The pedestrian warrant for a traffic signal is met when 4 hourly plots fall over the line in Figure 4C-5, or when any 1 hourly plot falls over the line in Figure 4C-7. The 1 hour warrant in Figure 4C-7 features higher threshold criteria, but requires that fewer hours plot above. When a signal is justified at an intersection by this warrant only, it will be actuated with pedestrian push buttons and pedestrian signal heads. If the intersection meets this warrant, but also meets other vehicular warrants, pedestrian push buttons would be installed unless the vehicular signal timing safely accommodates pedestrians in every signal cycle. A traffic signal without pedestrian signal heads cannot accommodate pedestrians unless the signal is set to interrupt conflicting traffic for a sufficiently long period of time. A pedestrian or group of pedestrians needs enough red time imposed on conflicting vehicles for the pedestrians to recognize and respond to their opportunity to enter the crosswalk, plus time to execute the crossing. Pedestrian signal heads provide a separate indication for the startup time, that's the walk interval. The length of the walk interval depends on perception reaction time, plus the number of PEDs and the width of the crosswalk. The flashing "Don't Walk" supports the pedestrian clearance time. PEDs who enter the crosswalk at the end of the walk interval need time to execute the crossing. The length of the flashing "Don't Walk" depends on the crossing distance, the walking speed, and local policy as to when pedestrians are permitted to be in the crosswalk. Some jurisdictions do not want pedestrians in the intersection during the vehicular yellow and/or vehicular all red. We will examine the implications of such restrictions in a moment. First, let's focus on walking speed and crossing distance. Here we take a look at walking speed and find that most pedestrians walk at a speed between 3.5 and 5.5 feet per second. While it is helpful to know the 50th percentile speeds as shown in this table, we ought to recognize that it is insufficient to design for the 50th percentile average user. Assumptions about pedestrian walking speeds continue to evolve with more current research and more explicit guidelines. We find that in 2004, John LaPlante and Thomas Kaiser were critical of the usual normal 4.0 feet per second design speed for the pedestrian clearance interval. They reported that the consequence of the 4.0 design walking speed was that as many as half of the pedestrians who began to cross at the start of the clearance interval may not have successfully cleared the travelway by the time conflicting traffic was released into the intersection. A related study of 15th percentile walking speeds was conducted by the Texas Transportation Institute, or TTI. The 15th percentile speed represents the speed at which 15% of the population walks slower, approximately 1 standard deviation to the left of the mean walking speed. TTI found that the 15th percentile walking speed was 3.77 feet per second for younger PEDs and 3.03 feet per second for older PEDs. TTI joined other researchers and recommended that the design speed for the pedestrian clearance interval be 3.5 feet per second for the general population and 3.0 where older PEDs are concerned. These reductions are reflected in the most recent editions of the MUTCD and the California MUTCD. Walking speed goes hand in hand with crossing distance when computing the pedestrian clearance time. The MUTCD says that the clearance time should be sufficient to allow a pedestrian who left the curb or shoulder at the end of walk to travel at a walking speed of 3.5 feet per second to at least the far side of the travel way. Two things to note: the end of walk, not the beginning, and to at least the far side of the travel way, and not necessarily to the opposite curb or shoulder. What is the traveled way? The traveled way is the portion of the roadway for the movement of vehicles, exclusive of shoulders, berms, sidewalks, and parking lanes. Let's take a look. Let's take a look at how the pedestrian clearance time relates to the walk, the flashing don't walk, and the steady don't walk. In this exhibit, we see the walk indication for the pedestrian startup, indicated here at 7 seconds minimum with a double asterisk to note that the walk interval may be reduced under some conditions. We see that the flashing don't walk or countdown indication is known as the pedestrian change interval. The pedestrian change interval is shown here in combination with the buffer interval to satisfy the pedestrian clearance time. The buffer interval is the portion of the steady don't walk prior to the release of conflicting vehicles, shown here to be a 3-second minimum. Pause and take time to study the figure, and note that we can go into the field to measure pedestrian intervals in operation and to observe how the pedestrian intervals overlap with the associated vehicular intervals. As with pedestrian signal timing, vehicle signal timing also features change and clearance intervals. For vehicles, the change interval is the yellow and the clearance interval is the all red. The change or yellow interval is set to allow a vehicle within one safe stopping distance when the green ends to continue and enter the intersection legally. The clearance or all red interval is set to allow a vehicle who has entered legally on yellow to clear its rear bumper from the travel lanes or crosswalks before conflicting movements are released. Roess chapter 21 defines each of these critical intervals and gives the motivation for proper selection of yellow and all red. Proper selection is motivated to avoid mistakenly introducing a dilemma zone. A dilemma zone is an area upstream of the intersection wherein, should the green be removed, a vehicle is too close and traveling too fast to comfortably stop, yet too far and traveling too slow to fully clear the intersection before conflicting flows are released. Equations 21.2 and 21.3 represent ITE recommendations for computing these critical values and avoiding the dilemma zone. Longer yellows are typically associated with higher speeds. Consistent use sets driver expectations. Thus, it is important that yellows remain consistent with driver expectation. This example from the textbook is an application of equation 21.2 and 21.3 for selection of suitable yellow and all red intervals. Pause and take a moment to study the diagram for the width of the intersection as far as pedestrians are concerned, and the other parameters specified here. Also in Roess chapter 21, we find a methodology for determining the minimum pedestrian crossing requirement. This methodology comes from the Highway Capacity Manual. The first term gives the minimum startup time of 3.2 seconds. The second term gives additional startup time based on the number of pedestrians and the width of the intersection. The third term is the crossing distance divided by the speed. Pause and take a moment to study the form of the equation, noticing that the top equation in 21.15 is for wider crosswalks greater than 10 feet, and the bottom equation is for narrower crosswalks. Also note 21-17, admitting that agencies have different requirements as far as when pedestrians may be in the crosswalk. Here is an example from the textbook applying the HCM methodology for computing the minimum green time for pedestrians. Pause and take a moment to observe the parameters and verify the computation.